having. So this phenomenon initially it was predicted by the scientist Meckel, and then after it was observed by the Sir C.V. Raman in the year 1928. We have. Okay. So the lines of low and high frequency sites, whichever we are of the Rayleigh frequency, that is the original one. So we will be calling it as what Stokes lines as well as the anti-Stokes lines we are going to be called. Okay. So which are having the higher frequencies than the original frequencies. We will be calling it as what we call Stokes and as well as the anti-Stokes lines respectively we are going to be called. Okay. So the scattered photons having the frequency shifts around 10 to 4,000 centimeter inverse, which is the characteristics of what we call vibrational as well as the rotational photons. So that means whenever these are interacting with the matter, so it may be takes place like vibrational as well as the rotational things it is going to be takes place. So with the help of that, the characteristic of vibrational or rotational energies of the molecules you are going to be have. Okay. So this is what generally the Raman scattering which we are going to be have. Now we will see the theory of Raman scattering in detail, how it is going to be happening. Okay, what is Raman scattering? How it is going to be happen? We'll see here. Raman scattering. So Raman spectroscopy here it depends upon the frequency of scattered light by the molecule. Okay, because they undergoes what like vibration as well as the they will be undergoing vibration as well as the rotation whenever this what we call radiation is interacting with the molecule. Okay. Suppose here, if you consider a monochromatic light, you know that monochromatic light means which is having the single wavelength or frequency. So when we'll take we'll be taking a monochromatic light. Right. So this monochromatic light, which is having what we call some frequency, nu we are going to be taken. So when this monochromatic light of frequency nu is directed at a what we call cell containing transparent substance, that is nothing but this radiation which is having the frequency, it is interacting with a transparent material. Okay, it is interacting with the transparent material. As we know that whenever it is interacting with the transparent material, most of the light or radiation which is going to be transmitted through this one. Okay, most of the light it is going to be transmitted through that substance, right? So, but some of the light which is not transmitted, that means which is not transmitted through the transparent substance, it is going to be what we call scattered. Okay, it is going to be scattered. The percentage of scattering is only around 0.1 percentage. Understand? 0.1 percentage. That means most of the light, whichever it is incidenting on that material, it is going to be absorbed by the transparent substance, but very few amount of light, around 0.1% of light, it is going to be scattered by the sample of the molecule in all directions. Understand? So this scattered radiation, which contains maybe having the frequency of nu, which is incident light. We said that nu is the monochromatic light which is incidenting on the transparent material. Nu is the frequency of that monochromatic light which is incidenting on the transparent material. As we know that some of the light, most of the light is going to be absorbed by that one. Very few percent, 0.1% of the light is going to be scattered. In that scattered light, it may be consisting of the same frequency nu. Okay, it may be consisting of the same frequency nu, and as well as it will be having the two other frequencies. Okay, two other frequencies. Okay, two other frequencies, which we will be calling it as what? One is nu minus nu 1, and another one we will be calling it as what? Nu plus nu 1. Understand? As we know that in the case of the Raman scattering, Raman observed that whenever the light is incidenting on that one, due to this inelastic scattering, very few, that is 0.1 percentage, it may be having the frequencies of original frequency nu, which is incident radiation, and also that it may be having the different frequencies, like two different frequencies, which is having the less frequency and some is having the more frequencies, which we call it as what? Stokes lines, and as well as the anti-Stokes lines. So here in special we will be calling it as the frequencies which is having the lesser than the original one. We'll be calling it as a nu minus nu 1, and the frequencies which are having the higher frequencies, which we are going to be call it as what? Nu plus nu 1 we are will be calling. So this is what observed by this scientist Raman. So which we will be calling it as what actually Raman scattering we are going to be called here. So suppose if you see that how this if you take this as the what we call a transparent material, if you take this is the transparent material which we have, right? So in this, what it is happening means here the incident radiation, which we will be calling it as the new frequency it is going to be have. Understand? So some of the most of that is going to be absorbed by this one, right? Some you are going to get the frequency out with the help of what we call same frequency, and some part which is scattering very less, that is a 0.1% like that, which is scattering out. So this scattered radiation, whichever we are going to be have, this is having the frequencies, original frequency nu in some case, in some other case, less frequencies, nu minus nu dash, and some other frequencies which are more than the original incident radiation, which we will be calling it as a nu plus nu dash we are going to be called here. Okay. So Rayleigh scattering is nothing but, which is actually the original scattering, which we are going to be called. The here it is given that Rayleigh scattering is around 10 to the power of -3 to 10 to the power of minus times intensity of light it is going to be have, right? And Raman scattering, which is having less than 10 to the power of -7 times intensity of the incident light. It is about the intensity of the light which we are talking about. So the Rayleigh scattering is having what? 10 to the power of -3 to 10 to the power of -5 times what we call intensity of the incident light you are going to be have. This is about the Rayleigh scattering, which is having the same what we call frequency, right? And in the case of the Raman scattering, it is having the less than 10 to the power of -7 times the incident radiation, which we will be calling it as what Raman scattering we are going to be called here. Okay. So now here, Raman observed that, okay, this Rayleigh scattering is a spectral lines whose frequency coincide with what? Incident light. Rayleigh scattering is nothing but what? This Rayleigh scattering is nothing but the frequencies which are having the same frequency nu. That is nothing but nu is nothing but what? The incident radiation frequency, which we will be calling it as what? A Rayleigh scattering, Rayleigh frequency or Rayleigh scattering we are going to be called. Okay. And however, he has been observed that the lines which are having the longer frequencies and as well as the shorter frequencies. One is having the, some of them is having the longer frequencies. Some of them you are having the what we call shorter frequencies. Both he has been observed. And he concluded that these lines arises what we call that is due to the incident light. Okay. So here generally the photons in terms of quanta, if you take, the we'll be calling it as E is equals to h nu. H nu is nothing but the photon, that is nothing but quanta of light. In quantum mechanically, if you take, we'll be calling that light will be measured in terms of quanta we are going to be called here. Okay. So this light, whenever it is interacting with the what we call substance, okay, whenever it is interacting with the substance, so it may be having both what we call rotational and vibrational energies. Okay. whenever it is interacting with the molecule in a such a way that it is going to be have what? Both, it may be having the what we call rotational energies and as well as the vibrational energies. It may be having both these rotational energies as well as the vibrational energies it is going to be have. Okay. Right. Suppose if you take the difference between the two vibrational as well as the rotational energy states is delta E if you take. Okay. The difference energy, the difference between the two vibrational or rotational energies is delta E if you take. That is the scattered photons having the energies. We can say that H nu 1, which will be equals to H nu plus delta E. Here it may be having plus or minus. Okay. So what is that? Energy of that scatter photons which are incidenting is H nu we are going to be called. Okay. So this energy of these you are going to be have in addition to the original one, E is equals to H nu plus delta E in one case. In some other case, it may be having minus delta E. It may be having H nu plus delta E in one case, and in another case, it may be having H nu minus delta E. Understand? Both it may be having here. So like it has been given that H nu 1 is equals to H nu plus or minus delta E, it can be given here. Okay. Now, if you take the form of the scattering in which the frequency of incident beam undergoing some changes, which has which are studied, which is studied by this Raman, we will be calling it as a Raman effect. That means the beam which is having which is scattered light, which is having the frequencies of different frequencies to original frequencies, which are studied by the Raman. This effect we will be calling it as what? Raman effect. We are going to be called here. Okay. And here, in the case of the what we call normal conditions, most of the materials of their lower energy levels will have a much higher population. Means which are present in the lower energy levels, which are having the higher population. So here, if you take in the first case, that is H nu 1 will be equals to H nu minus delta E. Okay. This is in the case which is having the higher population in the lower energy levels. Okay. In the lower energy levels. And the frequencies here, what we have? Original frequencies, new you are going to be have. In the lower energy levels, they are going to be observed brighter. Okay. They are going to be observed brighter. And these we are going to be called what? Stokes lines we are going to be called. Okay. These are, in fact, we are going to be called it as what? Stokes lines we are going to be called. So here, if you take the energy level diagram in this case, so here we have this is the change in its energy, delta E we are going to be called. So this is what the light is incidenting here. So before interaction here, this one you are going to be have. After interaction, what will happen? It is going to be give out certain amount of light energy. It is going to be give out some what we call some light energy it is going to be give. So this is going to be half energy, which is what we call E minus delta E is equals to H nu we are going to be called. Okay. This is going to be have lesser frequency to the original incident radiation. The lines which we are going to be called it as what? Stokes lines we are going to be called. What is that? Stokes lines we are going to be called. In some other case, what we are going to be have in which H nu dash, which will be equals to H nu plus delta E. In this case, the frequency of the incident radiation is nu if you take. The frequency of radiation of these lines, it is going to be have more than that you are going to be have. Because H nu plus delta E, it is going to be have. So in this case, what type of lines you are going to be formed? We are going to be formed what we call anti-Stokes lines. Anti-Stokes lines we are going to be called. Okay. Which we are going to be called it as what? Anti-Stokes lines we are going to be called here. Okay. So these intensity, if you take in the upper energy levels, they are going to be have less intensity than the what we call Stokes lines, whichever we are going to be have here. So generally, if you represent this So here if you see, so this is the original relic lines if you have, original one. So after incident of the material due to the inelastic scattering, we said that you may be having what we call lesser frequencies, which we'll be calling it as what? Stokes lines we are going to be called here. So this is lesser frequencies, which we are going to be call it as what? Stokes lines we are going to be called. And this is the incident radiation actually, which is a Rayleigh we are going to be called. And another case which you are going to get anti-Stokes lines, which are having the higher frequencies than this one. Than this one. So these we will be calling it as what? Anti-Stokes lines you are going to be. So original one will be having certain frequency of incident radiation nu here. So in this case, it will be nu minus delta E you are going to be have. And in this case, it is going to be have nu plus delta E. Okay, that is E is equals to H nu plus delta E. And another case, E is equals to H nu minus delta E you are going to be have. So these we will be calling it as what? Stokes lines we are going to be called. And these we are going to be call it as what? Anti-Stokes lines. So this is how the Raman scattering is going to be takes place. So what is Raman scattering we have seen is, so Raman scattering is nothing but whenever the light, some light is incidenting with the transparent material, most of the light is going to be, what we call it is going to be absorbed by that one. And some of the light it is going to be scattered. So the scattered percentage is how much? It is going to be have very less percentage, around 0.1% of the light it is going to be scattered. So due to the inelastic we will be calling it as inelastic we are going to be called. So in the case of this inelastic thing which is happening, so this Raman effect you are going to be observed. So that is what we call, you'll be having the lines of which is having the radiation is having lesser frequency in some other cases. Some cases you are going to be have more frequency than the original incident radiation. The frequencies which are having the lesser than the original incident radiation, we'll be calling it as the lines which are going to be formed as a Stokes lines we are going to be called, and the lines which are having frequencies more than the incident radiation, we will be calling it as what? Anti-Stokes lines we are going to be called here. So this, whatever the Raman scattering, they have been observed in a what we call a high resoluted spectrophotometer. So if you take the, in general, normal spectrophotometer, if you take, so you will be able to see that the scattered light is also having certain what we call some band like this, it is going to be have, it is going to be observed. But if you observe this in the high resolution spectrophotometer, they observed that this is consisting of again two different lines like this you are going to be have. So one is having the lesser frequency Stokes lines we called, and another one having the frequencies, higher frequencies than the original one. We will be calling it as what? Anti-Stokes lines. And the phenomenon which we observed is nothing but what? Raman scattering we are going to be calling here. Okay. Next, we'll see the what we call a classical theory of Raman effect. Next one is a classical theory of Raman effect. Both we have like a classical theory of Raman effect we have, and as well as this quantum theory of Raman effect. Okay. So here in the case of the classical theory of Raman effect, so this classical theory will gives a good physical picture of the Raman effect it is going to be give. So here suppose if you take an atom or a molecule, so if it is placed in an electric field, understand? So an atom or molecule, whenever if you place in electric field, so what will happen means the electrons are going to be displaced and as well as the nucleus is going to be displaced. That is nothing but in general, the atom which when we have taken into a certain field that is electric field, automatically there will some changes. As we know that electron is negatively charged and nucleus is positively charged. So they're going to be displaced. So you know that electron being attracted by the positive charge, that is positive pole, and similarly the nucleus is positive charge, it is going to be attracted by the negative pole. Okay, due to that some changes it is going to be takes place. So whenever this attraction for this electrons, as this it is negatively charged and nucleus is positively charged, it is going to be attracted by the negative pole. Okay. So due to that, what will happen means it is going to be get certain induced dipole moment. It is going to be get some induced dipole moment. So we know that dipole is nothing but what? It is a separation of the a positive and negative charges by certain distance. That is what we call it as a dipole moment. As we know that when we have placed certain atom or molecule in an electric field, the electrons are revolving around this nucleus which are negatively charged, so which is attracted by a positive pole, so which is going to form a dipole. And similarly, the nucleus is positively charged, which is attracted by the negative pole. So again, it is going to be formed as a dipole moment, dipole. So due to that dipole, okay, due to the dipole, so it is going to be produce certain what we call a dipole moment. Okay, so some induced dipole moment is produced in the molecule. Why? Because due to the displacement of this nucleus as well as the electrons. Nucleus is nothing but positively charged here. So then whenever it is induced by this dipole moment, we can say that the molecule is said to be polarized. What we can say that the molecule is said to be polarized. Due to the induced dipole moment, we can say that the molecule is said to be polarized here, right? So now here, in this case, we said that the electric field, whichever we have been introduced into a molecule or atom, we can say that the electric field, whichever we are introduced is E, we are going to be saying. Okay, E is nothing but the strength of the electric field, which we have been introduced this molecule or atom into the molecular atom. So, and mu here, mu, which we'll be taking it as a magnitude of the induced dipole moment. As we know that due to that molecular atom is introduced into electric field, we said that it is going to be generate what we call dipole moment, and the magnitude of that induced dipole moment we will be taking it as what? Mu. And we know that this mu and E both are proportional to each other. That is, mu is directly proportional to E. That is, the magnitude of the induced dipole moment is directly proportional to E. So if the electric field strength is increased, then mu value is going to be increased. If the electric field strength is decreased, the mu value is going to be decreased. Both are in proportional to each other. Mu is proportional to E. So therefore, if I remove this, we are going to proportionality. So we are going to get mu is equal to some alpha E we are going to get. Mu is equals to some alpha E we are going to get. So this alpha is nothing but what? The polarizability of the molecule. What is that alpha we are calling? Alpha is nothing but alpha is polarizability of the molecule we call. Alpha is the polarizability of the molecule, right? So now, when this molecule is subjected to certain beam of radiation, that means what we are doing, we are incidenting certain radiation onto this molecule. Some radiation is incidenting onto that molecule. And we say that that incident radiation is having the frequency nu here. What is that? we are taking certain amount of radiation which is incidenting onto that molecule. That incident radiation is having frequency of how much? Nu is the frequency of that incident radiation. Okay. So now, whenever we introduce this, what we call some radiation onto that molecule, the electric field will experiences what we call due to that electric field. So it is going to be experiences what we call certain uh, force on that one. So which is given by E is equals to E naught sine omega t generally. E is equals to E naught sine omega t. So that sine, in place of omega, we will be writing it as what? 2 pi nu we are writing. 2 pi nu we are writing in place of omega, that is angular frequency. Okay. What we did, we have subjected, that is onto a molecule, some beam of radiation of frequency nu is incidented, which is in the electric field, which is experienced by this by the molecule, which is given by E is equals to E naught sine omega t, which we will be calling it as what? E naught sine omega 2 pi nu. In place of omega, we are writing 2 pi nu. So this one we will take it as equation 1 here, and this one we will be taking it as equation 2 here. Understand? E is equals to E naught sine omega 2 pi nu. And this E naught, whichever we will be having, which is nothing but the equilibrium strength of that magnetic field. E naught here, it is nothing but what? Equilibrium strength. It is equilibrium strength which we have. E naught. Right. So now, what is the equation 1? We have mu is equals to alpha E. Right. What is that? We have written E is equals to E naught sine 2 pi nu t. So we will substitute this E into the equation 1 we are going to be substitute. So now if you substitute that one, we are going to get mu, that is nothing but the magnitude of the induced dipole moment, mu, which we can write it as alpha. In place of E, what we can write? E naught sine 2 pi nu t we can write. E is equals to E naught sine 2 pi nu t. That is mu is equals to what we have got now? Alpha into E naught sine 2 pi nu t we have got. Right. So now the induced dipole which undergoes certain oscillations here. Okay. Induced dipole moment, induced dipole, it is going to be certain oscillations because it is going to be what we call taken certain amount of radiation. It is going to be undergo certain what we call vibrations. It is going to be undergoes here. Okay. So which is having the oscillation frequency of nu here, which is having how much? Oscillation frequency nu we have been taken. Right. Now here, by the classical theory, okay, by the classical theory, the oscillating dipole should scatter the radiation of the, what it is given, radiation of the identical frequency nu, which is frequency of the incident radiation. Understand? What is that? We are taking that some light is incidenting onto the molecule, which is having the frequency nu. And according to the classical mechanics, okay, this oscillating dipole should have, that is, should scatter with the radiation of the same frequency nu. Understand? So this is, we will be calling it as what? A Rayleigh scattering. That is nothing but if nu is the frequency which is incidenting onto this molecule, and it should be scattered, okay, the oscillating dipole, it should be scattered with the same frequency nu. This one, we will be calling it as what? Rayleigh scattering we are going to be calling. Means, here in the case of the Rayleigh scattering, there is no change in the frequency of the incident radiation and the scattering radiation. Understand? That is due to the classical oscillating dipole. We can say that both are having the same frequency nu here. That is one frequency. Already we, in the case of the Raman scattering, we have seen that nu, it is going to be have the same frequency. And moreover, in the Raman scattering, we said that in addition to this original incident radiation frequency nu, we will be having two other frequencies. in addition to this original frequency nu, we will be having two other frequencies, which we have been called it as one, we call it as a Stokes length, and another one we'll be calling it as what? Anti-Stokes length we have been called. So here we have, in addition to the original frequency, we will be having two two different frequencies which are having. One is shorter frequency and another one is having the higher frequency. So here in this case, we will be considering that the effect of vibration. So suppose the molecule is, we have taken is a diatomic molecule. That means it is consisting of two atoms it is consisting of. Okay. That is two nucleus it is going to be have. So whenever it is what we call some incident radiation is falling on that molecule, so automatically these two nuclei, they are going to be vibrate. Understand? These two nuclei, they are going to be vibrate. So the two nuclei vibrate along the line joining them. Okay, along the line joining them. Okay. So now what will happen means there the variation in polarizability, that is alpha. The variation in polarizability alpha with small displacement in equilibrium, which is given by, what is that? Alpha is equals to, what is that? Alpha naught plus beta into x by a here. Understand? So here, what is that? Whenever this radiation is incident onto this molecule, the nucleus of those molecules undergoes what? Vibrations here. Okay, it is going to be undergo vibration. So automatically what will happen? Before that vibrations, it is having certain polarizability. After that, taking that incident radiation, it is going to be vibrates and its polarizability changes. Okay, its polarizability will going to be changes. So the variation in polarizability alpha with small displacement x here is given by what? With small displacement x from equilibrium position is given by alpha is equals to alpha naught plus beta into x by a, here it is given. So here alpha naught, whichever we have, this alpha naught is nothing but the equilibrium of the polarizability. Alpha naught is equilibrium polarizability we have, and beta is nothing but the rate of variation of polarizability with displacement. What is that beta? The rate of variation of the polarizability with displacement we have. And this A is nothing but the amplitude with which the molecules of the atoms vibrated. A is nothing but what? The amplitude of the, what we call molecules, atoms with in the molecule which is vibrated. That is a variation in the amplitude. We can say that A is what we have, right? Now here, as we know that whenever the incident radiation is falling onto this molecule, we said that it is going to be vibrates. Now the molecule will execute what we call simple harmonic motion, okay, which is going to be execute simple harmonic motion with certain displacement, and that which is given by x is equals to a sine omega t, which will be calling it as a 2 pi new vibration t, because due to this vibration only you are going to get. So that is what we are writing here, nu is equals to new vibration. So the simple harmonic motion of the molecule which is executing, right? The with the displacement x is given by what? X is equals to a sine 2 pi new vibration t we have been given here. Okay. So where new vibration is nothing but what? That is the frequency of vibration of the molecule, whichever we have. Okay. So we have got x is equals to this one. So already we have that alpha is equals to what we have? Alpha naught plus beta into x by a we have. So here if you substitute there in place of that alpha, alpha is equals to alpha naught plus beta as it is, we'll write. X is equals to what we have? A sine 2 pi new vibration into t by what we have? A, right? So this A will get cancels. Now alpha becomes what? Alpha is equals to alpha naught plus beta into sine 2 pi new vibration t you are going to get. Okay. alpha is equals to alpha naught plus beta into sine 2 pi nu vibration t you are going to get. So now we have got this alpha. This alpha we have to substitute in the previous equation, that is in place of mu is equals to alpha E naught sine 2 pi nu t, whichever we have written. So therefore, if we substitute there, what we are going to get, mu is equals to, we have alpha. In place of alpha, what we have got here, this alpha naught plus this one we have got, right? Alpha naught plus beta sine 2 pi new vibration t into what we have, this E naught sine 2 pi nu t we have. Okay, sine 2 pi nu t here. So if you rearrange this, we are going to get it as what? First one, alpha naught E naught sine 2 pi nu t plus what you are going to get, this beta E naught. One we are going to get it as what? Sine 2 pi. This nu you are going to get. Another term we are going to get sine 2 pi nu t, sorry. Another term it is sine 2 pi nu vibrational t you are going to get. Okay, this you are going to get. So here, this term we can write it as it is alpha naught E naught sine 2 pi nu t as it is we are going to write. Now here in this case, beta E naught we will be taking it as same. And this is in the form of sine A sine B. So that we can write it as a half into cos of A minus B minus cos of A plus B. So half we have taken outside. And here we will be writing this as cos of, what is that? 2 pi nu minus nu vibration into T minus cos of, what is that? 2 pi nu plus nu vibration into T we can write here. Okay. So the magnitude of this polarizability, we have got it as what? Some value alpha E naught sine 2 pi nu t plus alpha beta E naught into cos of difference between the frequencies minus cos of sum of the frequencies we have got. Okay. So this is the case with which we have got it is with the help of only we have considered that vibrational, this thing we have taken, right? So now suppose if you take the what we call rotational effect of the molecule. Okay. Now we'll consider the effect of rotation of the molecule on polarizability we have to consider here. In the previous one, what we have taken, only vibrational thing we have taken. So during this rotation with respect to the electric field, orientation of the molecule will be changes. Okay. The orientation of the molecule will be changes. And therefore, the molecule is not optically isotope, which we will be calling it as what? It is going to be exhibit some different polarization in different directions. It is going to be execute here. So now in the case of this rotation of the molecule, due to the effect of the rotation of the molecule, we can write the variation of the alpha. Okay, variation of the alpha, we can write it as what? Alpha is equal to, we can write it as alpha naught here, beta dash we are writing, and sine 2 pi, in place of nu, it will be 2 nu rotational we are going to write into T. So this equation why we have written, by taking into consideration the rotation of the molecule, we have written alpha is equals to alpha naught plus beta dash sine 2 pi 2 nu rotation into T we have written here. Okay. So here actually the rotation will takes place certain angle. Okay, through certain angle, that is pi degrees. That is nothing but the total angle with which it can be rotated. That is 360 degrees it can rotate. So pi is the angle, right, which will bring the data molecule into a position. After rotation, again, it will come back into its original position. It is going to come back here. And its polarizability is having the initial value. And here you can observe that in place of nu, we have written what? two new rotation we have written. What is that we have written? Two new rotation we have written. Why we have written that is because the polarizability change is twice as great as rotation. Here in this case, when we consider that rotation of the molecule, if you consider, in this case, the polarizability changes is twice as great as rotation. That means two times the new rotation it is going to be have. So that is the reason why we have written in place of new, two new rotation we have written. So in place of new rotation, what we have written? Two new rotation we have been written here. So now again, by taking the previous equation into consideration, that is mu is equals to alpha E. So we can write here mu is equals to alpha. In place of alpha, what we have here, this one. And in place of E is equals to E sine 2 pi nu t. So if you write and rearrange those equation, we are going to get it as what? This alpha naught. We have to substitute both. What is that? Mu is equals to alpha E is there, right? In place of alpha, we can substitute this alpha naught plus beta dash into sine 2 pi 2 new rotation t, we have to substitute. And in place of E, we have to write this equation 2. That is E naught sine 2 pi nu t, we have to write. So if you rearrange those, we are getting this one. That is alpha naught. What is that? E naught sine 2 pi nu t. That is first term. And next one will be beta dash E naught sine, we will be getting one term as 2 pi nu t, and another one we are going to get it as what? Sine 4 pi we are going to get. Okay. New rotation t we are going to get. And again, this if you rearrange by using that equation, that is sine A sine B. So we can write the first term will be as it is alpha naught E naught sine 2 pi nu t you are going to get, plus the second term will be as half beta dash E naught, and here we'll be having cos of 2 pi, difference of this what we call frequencies, minus cos of 2 pi, the sum of these frequencies, new and two new rotation into t. So here also it will be two new rotation only. Okay, this you are going to get. So from this equation, the frequency of Raman, what you are going to be have in this case, due to the rotation. In one case, we have what we call new minus two new rotation we have. Understand? One frequency, you see cos of 2 pi new minus two new rotation is there, no, here. So this is one frequency we have. And another frequency what we have got here, new plus, okay, new plus two new rotation we have got. So therefore, if you take the Raman shift, if you want, so the change in these two, like new plus two new rotation minus mu if you take. So the Raman shift is 2 times new rotation. So that is nothing but what we can say that actually in the case of the Raman effect, we observed that you are going to be have the Stokes lines and anti-Stokes lines. So which are having the lesser frequencies, we call it as what? Stokes lines we have called. Which are having the higher frequencies, we have called it as what? Anti-Stokes lines. So here, this is what we have been proved with the help of this classical theory of Raman effect. Understand? This is how we can prove with the help of this classical theory, the Raman effect can be proved. So Raman effect and we are going to get both in addition to the original, we are going to get two lines. One is having the lesser frequency, another is having the higher frequencies. So here, this is what we having the lesser frequency, then the original, and this is the higher frequency. In the previous one also, we have got two things. New minus new vibrational we have got, another one new plus new vibrational we have got. That means either whenever the molecule is undergone certain incident radiation, it can take place both rotational as well as the vibrational. So when rotational it has been taken place, we have got two frequencies. And in the case of the vibration also, we have got two frequencies. That is what the Raman effect has been proved, what we call classically. This has been proved. So this is what we have, classical theory of Raman effect. Okay. Now we'll move to what we call quantum theory of Raman effect. So in that you have like in book it is given only new rotation. You make it correction as a two new rotation. In the case of this what we call rotational frequency. In the equation 18.8. Next we'll move to quantum theory of Raman effect. Quantum theory of Raman. So we know that when we have studying about the quantum theory, generally we know that the light, whichever we are going to be take, that is going to be fall in the form of, like in the form of quantas, not continuously, but in the form of quantas. That is a discrete uh, thing you are going to be have. So here we know that what is Raman effect? That means some amount of radiation which is incidentally onto a molecule. So which is scattering. Due to the scattering, you are going to be have two different lines we have been called. So here we will take some beam of light which is falling on a what we call some molecule here. Okay. So what we are taking here again some beam of light or some radiation which will be incidenting onto this what we call a molecule. Okay, which is having certain frequency nu or whatever it may be. So which is going to be fall onto a molecule. So now here the light here we have to consider in the form of photons here because it is a quantum theory of Raman effect. We have to consider the light which is incidenting is photons, and that photons which is incidenting onto this molecule which are having the energy E is equals to h nu. Understand? The photons which are incidenting onto these molecules are having energy h nu, right? So these photons which are having this energy E is equals to h nu, these are going to be interact with the molecules. Okay, it is going to be interact with the molecules, and here two things can be happen. Already we have seen that is some of them will be deflected, that is nothing but the scattered radiation photons. That is, whenever this incident radiation is falling onto this molecule, one thing what it is going to be happening, the elastic collision. Due to that elastic collision, the deflected photons will have the same energy as the incident photons, right? So due to the elastic collision, due to this elastic collision, the incident photons and the reflected photons both will be having the same energy. Understand? What is happening here? One case, the incident photons and as well as the reflected photons both are having the same energy, which is E is equals to h nu we are going to be. That is one case. In another case, in which the inelastic collision is going to be takes place. What is that? Inelastic collision is going to be takes place. So in the case of this inelastic collisions, the deflected photons, that means which are falling onto that one and they'll be coming back. So the deflected photons will have either higher energy to the original one or the lower energy to the original one. That is, the deflected photons may have higher energies than the incident photons, or it may have the lower energy than the incident photons. It is going to be takes place. This is going to be happen in the case of the what? Inelastic collision. Inelastic collision. In the case of the inelastic collision, the incident radiation, whichever it is falling onto that one. So the deflected photons, if you take, this may be having the higher frequency than the original one, that is the incident one, or it may be having the lower energy. Okay. So they are going to be higher or lower energy than the incident photons you are going to be have. Okay. So this can be explained with the help of what? Kinetic energy of the photons. And the molecule means what will happen means the total will be same as it is. The incident and reflected both are having, means after reflection or before reflection, the energy whatever it may be, it is going to be have the same energy. That is due to the conservation of energy law. It may be having the same. That can be written as what? H nu plus E, which will be equals to H nu 1 plus E1. That means before incidenting onto that molecule, after incidenting onto the molecule, it should have the same energy due to the conservation of law of energy, which we can recognize what? E plus H nu is equals to E1 plus H nu 1 here. And here we have like E and E1. Okay. Here E and E1 are the rotational and vibrational energies of the molecules before and after collision. What is that? E and E1 are the rotational and vibrational energies of the molecule before and after collision. Why? Because due to the conservation of law of energy, before collision and after collision, it should have the same energy. So that is the reason why we have written E plus H nu is equals to E1 plus H nu 1 we have written, where E and E1 are nothing but the rotational and vibrational energy of the molecules we have. So if you write this equation and if you rearrange, we are going to get it as what? E minus E1 by H, which will be equals to nu minus nu 1, we can write. Because if you take this E1 to this side, it will become E minus E1. And this, if you cross multiply, we'll get the same. That is H nu minus H nu 1, which we can write it as E minus E1 by H is equals to nu minus nu 1, we can write it. Okay. Nu minus nu 1, we can write. Okay. So now the scattered radiation. Okay. Now the scattered radiation, if you take, so the scattered radiation can be classified. That means after hitting that molecule, it may be having the original, what we call energy of the incident radiation. And in addition to that, you will be having two energies. So that we can write it as E is equals to, we can write it as a E1, in which the frequency is also same, nu is equals to nu 1. This one will be calling it as what? Rayleigh scattering again. We'll be calling it as what? Rayleigh scattering. Rayleigh scattering is nothing but it is having the same energy or frequency, which we'll be calling it as with the what we call incident radiation, which we'll be calling it as Rayleigh scattering. And also we will be having two more energies, which is higher than the original one and lower than the original one. So E is greater than E1. E is nothing but what? The energy of the incident radiation. E1 is nothing but after deflecting back. So here in this case, E is greater than E1, in which the frequency will be less. Nu is less than nu 1, we can write. This is one case. And another case, the energy of the incident radiation is less than the energy of the reflected. That means scattered radiation, in which nu is greater than nu 1 you are going to be have. So these two cases, we will be calling it as what? Raman scattering we are going to have. In these two cases, we will be calling it as what? Raman scattering we are going to become. Because we studied that Raman scattering, it is consisting of, in addition to the original, we will be having the lower frequencies as well as the higher frequencies. That is what we call it as a Raman scattering. Okay. So that if you take this Raman scattering case, the energy is either given to take or taken away from the molecule, which is like this you are going to be have. So as it is given in the figure. Right. So initially what we have is, so the energy of the incident radiation is h nu. Okay. Here in this case. Okay. Which is E is equals to h nu. After this incident, okay, which is calling it as h nu 1, we are going to be called. So in this case, what it is happening means less frequency, which we'll be calling it as what? Stokes lines. We'll be calling it as Stokes lines we are going to become. And another case, what we are going to be have? Here is the incident radiation, which is having E is equals to h nu, and it is going to be moved to this level. Right. After incidenting, what will happen means, sorry, here. From this level to this level. So, and after incidenting that one, it will be having, this is the radiation, and energy is Hd1. So here in this case, what it is happening means, you are going to get higher frequencies than the Stokes lines. This one, we calling it as what? Anti-Stokes lines you are going to get. And in any case, original will be as it is you are going to be have, which we will be calling it as a Rayleigh scattering you are going to be have. So these are the two things which is going to be takes place. Okay. So in one case, what it is happening, it is having the lesser frequencies, and one case it is having the higher frequencies. Okay. So here it is what it is explained. That is in one case the Rayleigh scattering and the Raman scattering, which gives rise to Stokes lines. If the molecule is initially in a fixed excited vibrational state and returned to the ground state. This is also Raman scattering, which gives rise to anti-Stokes lines. Okay. So the intensity of the Rayleigh lines is much stronger than the Stokes lines and anti-Stokes lines. Okay. Rayleigh scattering intensity is much stronger you are going to be here. So this is what we call a quantum theory of Raman effect. Okay. ఒకటి స్ట్రోక్ తో ampere. The intensity of the Rayleigh lines is much stronger than the Stokes lines, which are much stronger than the anti-Stokes lines. In one case, it is Stokes lines. In another case, is anti-Stokes lines. First one is Stokes lines, and the second one is anti-Stokes lines. అంటే ఇది ఇది ఓకే, దిస్ ఇస్ ఓకే. ఇదేమో ఇంటెన్స్, దిస్ ఇస్ ఇంటెన్సిటీ ఆఫ్ ద Right. So this is what the quantum theory of Raman effect we have. Next, we'll see what is that polarization of the Raman scattered light. Next, polarization of Raman scattered light. Polarization of Raman. Hmm. So this polarization of Raman scattered light is for short answer only. Okay. So this Raman scattering, we take this Raman scattered light. So this Raman scattered light, it is found to be plane polarized. Okay. Is this Raman scattered is taken to be plane polarized light. Okay. So Raman scattered light is found to be plane polarized in different extents. Means in different cases, it is found to be what is that plane polarized light is found. Even if what is that excited radiation is completely unpolarized. Okay. Even in the case of the exciting radiation is completely unpolarized. That means the radiation which is moving from one level to another level, even that is unpolarized, the Raman scattered light is found to be plane polarized. It has been seen. Okay. So what it is given, if a completely plane polarized light is passed through a analyzer. Okay. So if you have a analyzer, this one, if you take, so what we are doing, if you take this analyzer, if you take, and we are passing this what we call plane polarized light through this one. Okay. This is the plane polarized light, and this is what we call analyzer. So whenever it is passing through a analyzer, the plane polarized light, so light will be completely extinguished, and when the axis of polarization of the analyzer is perpendicular to the plane. Right? The perpendicular one. Right. Plane of polarization. In another case, what we have is uh, plane polarized and will be allowed without decrease in its intensity when its axis is parallel also. Means there is no change in its intensity, they are saying. Okay. So on the other hand, what they are saying is if the light is only partially polarized, it will not be completely extinguished even if the axis is perpendicular to the plane of polarization. Okay. Two cases you have. In one case is it is completely coming out. In some other case, partial it is coming out. Even if you take what we call the axis is perpendicular to the plane of polarization. Right. So here what they have did is they have measured what we call degree of polarization. Okay. So which is given by the what we call depolarization ratio. Rho it has been given. Rho can be defined as I perpendicular by I parallel. Okay. I perpendicular by I parallel. So that is nothing but when we take this axis of polarization parallel, if you take, in one case what they have taken, the axis is perpendicular to the plane of polarization which they have taken. In another case, the axis is parallel to the plane of polarization they have taken, and the ratio they have measured, that is what we call it as a quantity, that which we are calling it as depolarization ratio we are calling. Perpendicular by I parallel, which we are going to be call it as what? Depolarization ratio we are calling. Okay. So here I perpendicular is the minimum and I parallel is the maximum intensity which is passed by through the analyzer. I perpendicular, actually it is given as I1, but actually it is I perpendicular. I perpendicular, it is the minimum, right? And I parallel is maximum you have, maximum intensity, which is passed by the analyzer. In one case, minimum intensity is passed through the analyzer, and in another case, it is passed maximum intensity to the analyzer. So for completely unpolarized light, both are same. Means if the light is passing through the analyzer, in both the cases, if the light is not analyzed, then I perpendicular is equals to I parallel it is given. Okay. When unpolarized light, in the case of the unpolarized light, I parallel will be equals to I perpendicular. So in that case, what will happen? Rho becomes 1. Rho is going to be 1. And for completely polarized light, I perpendicular will be equals to 0. So if it is 0, rho value is automatically 0 you are going to be. Okay, rho is equals to 0. And actually, this rho value, it is going to be vary in between 0 to 1. 0 is nothing but completely the light is polarized to the analyzer. 1 is in the case in which the light is unpolarized. So in between this 0 to 1, its value is going to be vary. In some case, partially, in some case, more light is polarized. That is what you are going to be have. Okay. So for intermediate degree of polarizations, in between 0 and 1, you are going to be have. Means some part partially or 50% or 75%, whatever it may be, polarized to this. Okay. So in general, this can be stated in an alternative way that fundamentals of totally symmetric vibrations gives the polarized or polarizability of the Raman lines, in which rho value is less than 6/7 we have. Okay. This, it is, sorry, greater than 1, 6/7. It is value is greater than 6/7 we are going to be have. Right. So the Raman line would be depolarized one, and rho value should be in between what we call 0 to 6/7 we have. Okay. So the line, the Raman lines, whichever you are going to be get, if it is polarized to a different extent depending upon this rho value. And in general, this can be stated in an alternative way that the fundamentals of totally symmetric vibrations gives polarized light or partially polarized lights, which is rho is less than 6/7. And if rho is greater than 6/7, if it is having non-symmetric vibrations, you are going to be get. Non-symmetric vibrations gives the this what we call depolarized Raman lines we are going to be called. So here actually the what we call measurement of degree of polarization, that is rho. Okay, rho is nothing but the measurement of the degree of polarization of a Raman lines. We will call rho is nothing but the measurement of degree of polarization of Raman lines. And this degree of polarization of Raman lines is therefore bound to what we call help the assignment of the Raman lines to the molecular vibrations and to determine the molecular structure. And depending upon that value, how far what we call the molecules are vibrating. So depending upon that, we can able to determine the structure of the given molecule. Okay, we can determine the structure of the molecule which we have. And polarization of the Raman lines is an important parameter in Raman spectroscopy. Okay, which is what we call it as polarization of Raman scattered light. We are going to pick up. So in this unit, what we have seen, first one, what is Raman effect? So if they are asking to explain the Raman effect, that Raman effect we have to explain. So generally, they may ask to explain the Raman effect in the short questions. Okay. Uh, Explain the Raman scattering with the help of energy level diagram. ఇది క్వాంటమ్ థియరీ ఇక్కడ ఉంది కదా మనకి స్టోక్స్ లైన్. ఫస్ట్ వన్ ఇస్ క్వాంటమ్ థియరీ ఆఫ్ రామన్ ఎఫెక్ట్ విత్ ఎనర్జీ లెవెల్ డయాగ్రామ్. ఎనర్జీ లెవెల్ డయాగ్రామ్ ఎప్పుడు వస్తుంది మనకి? when we study about only quantum effect only, quantum mechanics, that is nothing but we can say that the energy is not continuous, but it is discrete. Discrete is nothing but different energy levels we have. So when we are asking about the energy levels, it should be quantum theory of Raman effect. So we have to explain the quantum theory of Raman effect. So this quantum theory of generally this classical theory, combining the classical theory and quantum theory, they may ask for long question. Okay, and short question they may ask like what we call polarization. They may ask generally what is polarization? This rho value, that is the measurement of the degree of polarization which we have. That is polarization of the Raman. So in this unit, one long question you may get or one short question. In the previous unit, which we have IR spectra, you may have the long question like what we call spectrophotometer diagram, double beam spectrophotometer. You have to explain that may ask, and the vibration of the polyatomic molecules with example like a CO2 and H2O. Okay, different vibrations like stretching vibrations, bending vibrations, whichever they have. Okay, they may ask that one. So overallly in this unit, like what we call in these two units, you may expect one long question or two short questions, or two long questions, one short question from these two units, from the IR spectroscopy and as well as this what we call Raman spectroscopy. Okay. That is what we have. Previous questions, this will have this already. I shared no previous question papers. Go to that. Raman scattering. E is equals to h nu, that is in the case of the Rayleigh scattering. Uh, uh. In one case, frequency it is going to be decreases. In another case, frequency will be increases.
Depends on the changes in energy.
Huh? Uh. ఇది incident radiation. E. E1 is the energy after what we call incidenting scattered light. Scattered light. In the case of the scattered light, energy may be more or energy may be less. E is equals to h nu. E is
రెండు ఇన్ఫర్మేషన్ ఈజ్ ఈక్వల్ టు ప్రపోర్షనేట్ టు న్యూ కదా సార్. అయితే ఇక్కడ ఈ అనేది రెడ్యూస్ అయితే
but overall ఇక్కడ ఏమన్నా overally this energy will be constant. Overall గా
లా ఆఫ్ కన్జర్వేషన్
ఇక్కడ in one case it may be more, in case in automatically in one case more means automatically here you'll have less. The combination of this will becomes again equal. That is what here it is written. Here it is written.
According to the law of conservation.
So we left with like two more we have, like a rotational and vibrational spectra of the Raman. So rotational spectra in detail we have to study of the Raman spectra, and another one is vibrational spectra we have to study in detail. And vibrational spectra for CO2 molecule it has been given. And in another one what we have is laser Raman spectra, and difference between the Raman spectra and the IR spectra. Generally, it's a difference between Raman spectra and IR spectra. They are asking for short questions. This unit is for short questions mostly. Okay, this doubt same level. Maximum easy and understand it to do. Where comparatively others.